Okay, so what we want to do now is say a bit more about the curl, and note that up until now, we don't know what the curl means. At least what is the physics interpretation of the curl? What does it measure? Okay, and the reason I postponed this is because the ability to understand what the curl is depends on that understanding of the theorem that relates the curl to being a conservative field. Okay, so here's the idea. So the quantity, the quantity, or let's remove the word the quantity integral of f dot dr, line integral over a closed curve gamma, is sometimes referred to, is called the circulation of f over gamma. And why is it called that way? Remember that our motivating interpretation for this was work. Remember that? Why is it called the circulation? So if you think of the field F as representing a flow of water, for example, then here is a closed curve gamma, some closed curve gamma. So this is going to be gamma. And if F represents the flow of water, so if, for example, our F, I'm going to draw in blue the arrows of F. F is a bunch of arrows, right? That's why it's called a field. So suppose that F at this point looks like this, and let's say that at this point it looks like this, and at this point maybe it looks like this, and here it looks like this, and like this, and like this, and like this. I don't know, something like that. F can be defined everywhere, but at points on the curve, suppose it looks like this. This is the direction of the flow of the water. Then if you think of this curve, water is circulating around this curve. Can you imagine that? Okay, because the component of F in the direction of the tangent vector is non-zero at almost every point in this drawing. Maybe here it's almost zero. So the water is going to be flowing. Okay? If you think of a bead and you think of this as a wire, you can also call it circulation. That bead is going to go around that wire because at every point the force is going to be pulling it. Do you understand that? Okay, so this is why this quantity is called the circulation of F over gamma. What would a field that has these circulation over closed loops look like, in contrast to what would a field where closed loops have no circulation look like? So here are some examples. So if your field, for example, looks something like this. Suppose you're in a field whose arrows look like this. This is some area in the field, and this is what the field looks like. And suppose you put a closed curve here. Here's a closed curve. Is there going to be circulation on this curve? Okay, let's think for a minute. If we take, it's not true that at every point the field is perpendicular to the curve, which would obviously mean zero circulation because the component of the field in the direction of the tangent vector is zero. However, so at this point, for example, the field is perpendicular to the curve. But at this point, suppose the curve is oriented in this direction, doesn't matter. At this point, the field is doing work, right? It is in the direction of the tangent. However, for this point here, there's going to be a point somewhere here where the field is precisely in the opposite direction of the tangent line, contributing minus the amount that it's contributing here. Do you see that? And if you look at it carefully, and this is just an intuitive example, if you think about it, for every point here, so here f could contribute something to the circulation, but then here it would contribute something in the other direction, right? So the total will cancel out. Do you agree? Okay? So the total, here you have a positive contribution, here you have a negative contribution. Sorry, positive, negative. Positive, negative. Okay, clear? Because here the contribution would be just of this part of f, and here the contribution would be of the part of f in the direction of the normal. No, this is not what I wanted. I wanted to look at this point here. Here the contribution would be precisely something like this. Okay, so they cancel out. Clear? So there's, these are confusing. Anyway, do you understand what I'm saying? So there's going to be a cancellation of the contributions of the field at every point, and the total work, the total circulation, is going to be zero. Clear? So in a field that looks like this, the integral over the closed curve gamma of f is going to be zero. In contrast, if the field looks something like this, for example, I told you I have a weakness for drawing fields. It's so much fun. Okay, so if this represents the field, totally different, then if you take a loop now here somewhere, now this is gamma, then obviously there is going to be circulation along this loop. Do you see that? Okay, so the contributions are going to add up. Clear? So in this case, the integral of f dr over gamma is going to be positive. I forgot the dr here. Okay? So this phenomenon, again, this is a very intuitive discussion. I'm not formalizing stuff because we just want to understand the terminology involved. So a field that looks like this is going to have circulation on closed loops, whereas a field that looks like this is not. Okay? And remember, what we're discussing is the rotor. I don't know if you noticed, so looking for the rotor on the board, I just circulated in this field. Anyway, what we're discussing is the meaning of the rotor, and for that I'm going to go back to the theorem on conservative fields. If the rotor is zero, then the field is conservative. The field being conservative means that it has zero circulation for every closed loop. Right? So the rotor, the curl, measures circulation. If the curl is zero, then the field does not have circulation on closed loops. And the terminology is, so let's write that, if the curl of f is zero in some domain, and let's assume that f is C1 and that the domain is simply connected, so everything works out nicely, then the circulation over every closed loop is zero, because it's conservative for every gamma closed. Therefore, a field f satisfying satisfies that it has zero curl everywhere is called irrotational. That's the terminology. Okay, an irrotational curve. Moreover, there's more to it. If you remember, is this clear? Do you understand? Does the drawing, does this picture really say it all? Why a field that is not conservative, there are closed loops with non-zero circulation, you can see that it's rotational. If you put a bead here, it's going to, right? Or if you think of water, it's going to have, it's not going to be safe water to swim in. Let's put it that way. Okay, clear? Okay, but there's more to it. So what's the more to it? If you recall, when we discussed the divergence, we had an alternative definition for the divergence which didn't depend on the coordinate system or on f being C1. Okay, and it was some form of limit definition, and I want to do something very similar for the curl. Okay, so moreover, if we take, I'm going to do it more briefly than in the discussion of the divergence because it's very similar. So if we take the line integral over a closed curve, which I'm going to call gamma sub r, it's going to be a circle of radius r. Gamma sub r is a circle, a little circle with radius r. And by Stokes' theorem, we know that this equals the surface integral over the curl of f over a surface which we're going to call SR, which is going to be the disk, the little disk, which gamma r is the boundary of. Okay? So this is, the picture is, this is SR, and this is gamma r. And it's of radius r. Okay? So do you agree to this? Okay, this is Stokes. Now, remember what a surface integral is. A surface integral is the integral over the, let's assume that all of this is happening in the plane. Let's just look at a planar. It is happening in some plane, because I took a circle. So on this plane, let's assume that this is the xy plane. So everything is planar here. So the parametrization is going to be planar. So it's the integral on this same domain, okay? But what is the integral of a vector field? It's the integral over the domain of the field dot the normal. Okay, and now once you dot it, it's a line integral of a scalar function, a surface integral of a scalar function. Okay, so this is what it is. And this integral, you can think about it as it's really a double integral. This double integral by the intermediate value the intermediate value theorem for double integrals equals the value of this entire integrand at some point in the domain times the area of the domain. That's the intermediate value theorem. So by the intermediate value theorem, this equals the rotor of f dot the normal evaluated at some point, let's call it Q, where Q is some point inside this SR, times the area of SR, which is, of course, pi r squared. Right? And this leads, I'm going to erase up here so we can stay on the same board. This leads to the definition of the rotor. So we can define, it's an alternative definition, the rotor of f dot n, dot the normal, to be the limit as r goes to 0. So I'm looking at the two sides, dividing this by this, ignoring all the middle, dividing this by this. As I take the limit as r goes to 0, SR shrinks to a point, gamma r shrinks to a point, Q shrinks to the center of that disk, right? So what I get, so this at the point, some point P, is the limit as r goes to 0 of the line integral over gamma r, which is centered at P, divided by the area of SR, which is pi r squared. Okay, very similar to what we did with the divergence. Okay, so this is not exactly the rotor at the point P. It's the dot product of the rotor times the normal vector to the surface at the point P. Okay, and this definition leads to, so what do we have here? What is this thing? This we just said is the circulation, right? The line integral over a closed curve. And this is the circulation over gamma r divided by the area that gamma r encloses. Okay, so it's circulation per area. Do you see that? Okay, so this leads, so therefore, the rotor is thought of, this is not a precise statement, but it's thought of as the circulation density. Of F. How much circulation per unit area does F generate? Okay, circulation per area. Okay, that's circulation density. Clear? So that's the rotor at a point is the measures, or let's say the rotor of F, let's see, measures, that would be maybe more, the circulation density of F. Okay? And moreover, remember that we're dotting with the normal. Okay? So if you look at your field, when is the circulation going to be the greatest? When is the circulation going to be the greatest? When the rotor, when is this dot product going to be the greatest? When this vector, the curl, is parallel to the normal, right? Then their dot product is going to be the greatest because we're multiplying by the cosine, right? That's how we do dot product. So the circulation is going to be the greatest when the rotor is parallel to the normal. So if the rotor is pointing in the direction of the normal, then you're going to have maximum circulation, and therefore the direction of the rotor is called the axis of not circular, the axis of rotation. That's what it's called. Okay, so if you look at this is kind of a two-dimensional field in this board, but the rotor would point this way. That's the axis of rotation along which things are going to rotate. Okay, so let's add that. So let's add it here. The direction of the curl is called the axis of rotation. Clear? Okay. So all I've said in this clip is actually taking the observation that taking Stokes' theorem. Okay, taking the observation that when that a curl is really measuring circulation When the curl is 0, there's no circulation on closed loops. And when there is, we can actually think of the curl as the circulation density and the direction of the curl as the axis of rotation. Okay? And you should be able to, you maybe need to think about this for a bit more, but if you think of flowing water and the field representing the flow of the water, then you should see the physical interpretation of this notion of the curl. Okay? Okay. So it's not something that you're gonna use in this mathematical course, but in applications, these ideas are important. Okay, in applications they are important. Okay, so this wraps up this discussion of the physical interpretation and the meaning. And by the way, I forgot to say the most important thing: curl and rotor, both words, hint at rotating, right? At curling or rotating, and that's the reason for these words for this quantity, for this notion. Okay, so that's the end of this one. Okay, so